Hello students. So today we'll see about the challenges of IIoT. So this is the continuation of first unit. So we'll see what are the challenges basically in IIoT. So there are so many challenges in IIoT. So we'll see how it can be improved and what are the challenges. So first we'll see the introduction part. So moving on to the introduction part, despite this potential, research and development in IIoT and CPS systems, for example, cyber physical systems, are still in their development stage. So successful implementation of IIoT requires digital addressing. So it's a very tedious task, and there is an array of challenges across technical, organizational, data, and human dimensions. So, in both the systems, IIoT and cyber physical systems, it controls the networking facilities, and it has to enhance the performance based on the technology. So, here we'll see the technical aspects and the infrastructure challenges. So moving on to the technical challenges, so it is considered to be a primary challenge. So where we'll have various architectural patterns. So that can support a wide variety of hardware and software systems while maintaining manageable complexity. So a primary challenge is specifying an accepted extensible infrastructure or architectural pattern that supports diverse hardware and software while maintaining manageable complexity. So here we have different types of infrastructure. So it has to be maintained its complexity. So moving on to the next part, there is a lack of uniform processes guiding manufacturing operations management, wireless technologies, diagnostics and prognostics, and cyber security at all levels. So, integrating all these new technologies into existing operational environments requires updating all the old machines or devices. So establishing the digital communication standards that can orchestrate both new and old hardware. So the heterogeneity of production infrastructure from different supplier poses a significant obstacle. So here that's considered to be a challenge. So there is a lack of methods. So supporting composition among model components. So that has to be improved here. So the viewpoints basically it has to be improved along with the principal barrier to the integration part. So these are the obstacles we have seen in technical infrastructure challenges. So next coming on to communication and networking challenges. Here we can adapt transparent and adaptive communication. And the second part is standardization of communication. So already we have discussed about the standardization of communication previously. So now we'll see the transparent and adaptive communication. So it basically represents the modeling and design techniques. So that is required for these network structures. So that monitor and control physical production and manufacturing processes. So to improve the performance, so they basically use information delivery systems, robustness, and quality of service. So evolving these infrastructures along with CMS and IIoT, so raise a new challenge regarding communication part. So that's the major concern here. So respective of information exchange, they have transparent and adaptive communication, so that has to be improved. So it should also guarantee real-time delivery of information. So these particular part are considered to be the challenges here. So and other aspects of quality of service has to be improved. So furthermore, we have to consider a decentralized system. which needs a higher level of automation. So automation should be a challenge there. So higher level of automation regarding self-management and maintenance can be the major issue here in transparent and adaptive communication. And moving on to the standardization of communication, it is a decisive factor. While using protocols like OPC, UA, MT Connect, and MQTT, so these particular infrastructure along with CMS and IIoT raise new challenges regarding communication. So here we consider um, physical objects communicating, which is still largely absent, leading to incompatible approaches. So here in artificial intelligence and analytics, so it has to be established to facilitate self-management techniques and diagnosis capabilities. So here, beside all these techniques, new optimization potentials has to be enhanced, and it can be revealed by making new use of enormous amount of gathered data. So, yeah. So moving on to the next part, communication and networking. So we'll see what are the things needed for communication. So current wireless technologies like IEEE 802.11, Bluetooth are often unsuitable for industrial automation. Due to its insufficient latency and reliability guarantees, it is very harsh in industrial environments. However, current standards for wireless communication such as IEEE 802.11 or Bluetooth are not suited for industrial automation. Both in latency and reliability, it has to be enhanced. So it is just necessary to develop new standards targeting mentioned guarantees, at the same time providing interoperability to other services envisioned in the IIoT that do not rely on such communication standards. So internet utility for CPS systems is limited. So by the high heterogeneity of commercial networks, diverse operator or QoS policies, there is an insufficient communication reliability. So this tactile internet imposes very limited requirements on communication infrastructure. So that should be an issue here. So that might not be supported by existing technologies and demands, and the development of the capable ones. So, however, the requirement of decentralized networking of CPS systems and smart products involve risk. Involving this risk can be considered based on the robustness of the production. These has to be enhanced. So basically, the safety and security risk has to be handled properly. So it's remain an open question to address this contribution. So next we'll move on to modularity. So achieving modularity based on plug and produce capabilities is adapted here. So it supports open and standardized interfaces, which provides an area for recurring future research and market development. So especially given by the prevalence of high individualized and protected interfaces. So next we have data management and analytics challenges. So in data management and analytics challenge, we have data volume and quality. So we'll see what are the challenges in transforming raw data into smart data. So next is based on data quality, and next we have processing and knowledge. So we'll see in detail about data and data volume and quality. So one of the challenges is the interconnection of the data. So there is exponential increase in data volumes generated by sensors or other devices. So it requires specialized industrial data warehousing solutions. So a huge amount of data volumes exist without any connection to other data. So the challenge is a big issue here. So big data concepts are used is used to connect data to gain competitive advantages and savings and to form a new business. So, considering the data warehousing, every data has to be stored and it has to be analyzed which part of the data is needed. And there are a large volume of data which is doubling every 2 years. So, this has to be compensated, and this has to be the major concern in data management and its challenges. So, however, providing technical systems together to store and analyze raw data is not sufficient and does not lead to the expected big breakthrough in information processing. So, no matter how much data is available, additional context information like time, structure, and location. So, it is necessary to enable the transformation of raw data into smart data and providing the necessary information base to extract new insights by applying suitable analysis algorithms. So next we go to transforming raw data into smart data. So this requires additional contextual information such as time, structure, and location. So along with context-aware analysis algorithms. So such transformation from raw data into smart data requires context-aware analysis algorithms. So it provides data accessible and interpretable for users and machines. So next we'll go for data quality. So data quality is a critical success factor. So it also considers some challenges like synchronizing data from heterogeneous sources and handling issues such as low sampling rates, unsynchronized or patchy data, jitter, and based on latencies. So here, if you consider the analysis of historical processes, data throughout the product life cycle requires new architecture and platforms. So this enables enormous volume of data, and the variation and speed of data is a major concern here. So the data analysis drives the conventional data acquisition and storage to their limits. That is why big data platforms are needed nowadays. So next, moving on to the processing and knowledge. So processing massive amounts of data, which is always stored in cloud and can be hindered by limited bandwidth. So the fundamental challenges faced by faced by these processing and knowledge is to identify the opportunities for provide improving performance and integrating new smart technologies. So while improving these particular parts, we can improve the processing and knowledge capabilities in data management. So this can also be improved based on these particular methods. So industry routine collects operational level data of all kinds. So there is a lack of specific knowledge required to effectively use operational data for overall performance improvement. So this is all about the processing and knowledge. So data management and analytics challenges are considered to be data volume and quality. And second, it is based on transforming data into smart data. The third is based on data quality, and fourth, it is considered to be processing and knowledge. So next we'll see challenges in cybersecurity and reliability challenges. So, considering all the cybersecurity and reliability challenges, so there is an increased value of network system nowadays, which also brings increased vulnerability to cyber threats, including data theft, security issues, privacy issues, and so on. So, in the event of a successful outcome of these digital attacks, the negative consequences are to be considered. For the affected companies are very much concerned with the data and its management. So these privacy issues, safety issues has to be considered, and it has to be enhanced without any malfunctioning of interconnected machines in industries. So the range includes malfunctioning of machines, endangering the work safety. It reduces the customer's confidence. So these particular challenges are very alarming nowadays. So the consequences underline the need for reasonable cybersecurity solutions. So, ensuring the safety and security is a crucial success factor for Industry 4.0. So, it includes safeguarding data and intellectual property and ensuring CPS components do not pose a danger to employees or customers. So, these are the major concern, and the reliable security is also a major concern. It should consist of measures both on individual and system participants level as well as on the overall systems level. So moving on to the next part, for direct cooperation and interaction between personnel and machines, manipulability needs to be eliminated, which requires the engineering of robust safety system infrastructures. So this involves direct cooperation and interaction between personnel and machines, which has to eliminate manipulating the data, which requires engineering of robust safety system infrastructures. So these are the major concerns in cybersecurity and reliability challenges. So moving on to the next part, it is system integration and architecture. So basically you should know what is meant by integration. So integrating all these sub parts is considered to be integration. So we'll see basically about the system integration and its architecture and what are the major challenges in integration and architecture. So, considering integrating IIoT into existing infrastructure, so integration with various subsystems are possible, and new systems are often constructed by integrating various subsystems. So, if you have heterogeneous production infrastructure from different suppliers and implementing new systems into existing machinery, so there is various hardware and software subsystems that has to be integrated. So, as a typical example, a vehicle control system can be considered here. So, it is composed of hardware and software subsystem, which is supplied by the different vendors. So the integration of subsystems designed by various manufacturers often requires redesign. So redesigning the system will make changes in the entire system design. So redesigning the system interface. So it remains an issue for cyber manufacturing systems, particularly in transfer printing with high expectations in robustness, real time, and in multifunctionalities. So these challenges has to be rectified here. So current production lines, so it involves rigidly linked production lines which prevent quick challenges to the production sequence. So that can also be adapted. So this inadequacy represents individual machines, example for like due maintenance intervals, which result in entire line and significantly impairs the overall effective equipment effectiveness. So it has the major challenge. So it can affect the overall equipment effectiveness. So that we call it as OEE. So the specification of generally accepted extensible infrastructure or architectural pattern is a major challenge here. So, for example, you can consider so many use cases. So, showing the inflexibility of current assembly lines is the reworking process. So, the rejected products are not discharged automatically. So that can be considered as a challenge. So discharge automatically manufacturing line and transported reworking stations are to be considered. So further major challenges are like extensible infrastructure or architectural patterns that do not support a variety of sensors, actuators, and other hardwares and other software systems. while on the other hand, the complexity of the system has to remain manageable. So, considering this type of network system, it contains only a small scale sensor device, but should be manageable with planning systems, and it should give access to the enterprise information. So these enterprise information should be highly aggregated key performance, which should also indicate overall equipment effectiveness, or a bulk of information like stock of components, parts, and products can also be considered here. So, in order to manage all these various systems and to provide a new way to satisfy the information demands, so researchers are still working and have introduced some concepts like pseudo-standardized architectural system patterns, which is used in the past. So the automatic discharge of rejected products for reworking has to be improved, and this will enhance the system integration in future. So next we go for system integration. The third step is design patterns for service-oriented and cloud-based architectures. So new design patterns are adapted here, and service-oriented and cloud-based architectures are used. For such architectures, they have used design patterns, which is pre-verified, and it is reusable solution to a common problem in CPS systems. So they are yet to be identified, and it has to be defined properly. So, and migration aspects must be covered here. So, thereby, especially enhancing the domain of production systems, migration aspects have to be implemented, and it can also be improved based on CPS systems with defined and identified reusable solutions. So, moving on to the next part. So, lack of methods to support composition among model components. So, some viewpoints is a better principal barrier to integration. So, in addition to all these, creating analytical models, there are fundamental challenges to actually represents making use of information from various sources, and challenges also include like knowing the techniques to be applied, which is very appropriate to the situation. And moving on to the next challenge, we can have support composition based on knowing the extent to which the analytical results are valid, and based on acting on the insights to the effort. So these consequences include missed opportunities, and it creates reuse knowledge, unreliable results, and high cost of analysis can be a major concern. So currently, the models and the information sources used in analytical activities are not easily integrated. So there are so many barriers to this integration part. So a principal barrier to integration is a lack of method that support composition both among model components and disparate viewpoints. So, when you consider existing research which does not take advantage of unique characteristics of smart manufacturing, so a viewpoint is a set of related concerns here, so which draws a representation of the whole system. So these all characteristics include ongoing need for analytical methods, the integration part with the data from operations, the integration with the production, control systems, and etc. So this ability to dedicate a portion of manufacturing resources to experimental investigation of new processes can be adapted, rectifying all these challenges. So these particular challenges, if they are addressed, then experimental investigation of new process will be easier in future. So next we'll move on to real-time performance. So ensuring real-time feedback for effective interaction between communication and physical processes is critical. But suitable programming languages are considered, and concurrent software are not readily available for real-time performance. So, in real time, the control of the communication based on software needs to be aligned with the time lapse in the physical world. So the computation is expected to provide real-time feedback for effective interaction between the computation and physical process. So, however, there are no such programming languages and no concurrent software available for this purposes. So that's the major concern for real-time performance. So it is still unclear to degree real-time requirements to consider high transmission speeds and low response times. So these has to be enhanced in future. So when designing a cyber security manufacturing system for transferring operations to ensure real-time control for each manufacturing steps, with all these limitations, it can be even more difficult to address. So all these particular challenges has to be rectified. And moving on to regulatory and legal framework, it considers new complexity of digitalization, so that cannot be mastered through existing regulatory frameworks. So data protection should be the major concern here. Data ownership, privacy, security issues, everything are considered here in regulatory and legal framework. So the new complexity of digitalization cannot be mastered through existing regulatory frameworks. So modifying regulatory frameworks will have to fulfill certain requirements such as data protection, and it should have flexibility to utilize the potential benefits of new and rapidly changing technologies. So there is a need to address issues like data ownership and data access, data protection, etc. So finding answers regarding all these social implications are very crucial. So even though there are multiple examples for successful smart grid implementations, there are still major issues and challenges that need to be faced. So when it comes to smart grids, one of the most critical aspects are the questions of data ownership and access among the utilities of various energy sources, as limited information is available in public. So, considering all these factors, improving the grid security, and furthermore considering grid security, it needs to be considered under completely new aspects. So, complex subjects can also be resolved. Another complex subject is to resolve the question of the smart grid operation guidance. So, the role of these individual components, such as wind energy, for example, say, which is used in smart grids, needs to be defined exactly in the order to keep the system's power quality, reliability, and cost effectiveness. So, therefore, standards needs to be defined in order to enable proper communication between the individual parts. So, this often illustrates an economic state analysis, and there are some subsequent recommendations here. So, the recommendations can include creating and fostering innovation ecosystems. So the role of individual components has to be enhanced, and systems power quality, reliability, and cost properties are the major concern here. So next we'll move on to implementation and research challenges. So first we have maturity and standardization. So here, if you consider integration of new technologies, it often requires an update of existing mission fleets rather than building completely new facilities. So, however, in these particular fields, we have so many current trends nowadays. So, newer versions are invoked, and there are some difficult strategies to achieve all these maturity and standardization concepts. So many attempts to create a common standard, basically for industrial scenarios, have been made, but so far none was able to spread throughout the industry. So, therefore, a brief overview of technologies connecting physical objects with computational element is given here to put the presented ideas into context without a claim to completeness. So next we'll see a fragmented and disjoint standards landscape for wireless network which exists. So here the limitation of wireless network has to be considered here. So when you consider wireless network, so it has very limited communication bandwidth. Frequent disconnections are also possible. So heterogeneity of fragmented networks can be a major issue here. And other than these, we have limitations imposed by mobility. Route breakages are also possible. Lack of mobility awareness by system of applications and limitations of the mobile device, and short battery lifetime, limited capabilities are possible in wireless networks. So these are the major challenges. So achieving this openness and standards of interfaces in existing interfaces is represented, which provides an ongoing research and market development issue. So, the need of achieving openness and standardness of interfaces is very useful nowadays, but it has to be improved in implementation of IIoT manufacturing devices. So next we'll move on to the integration of new technology. So I told you already. So new technologies can also be adapted to integrate all these subtasks or sub-processes. So it requires an update of existing mission fleets rather than building completely new facilities. So next we'll move to complexity management. How do you manage its complexity? So that is a major concern in IIoT. So the growing complexity of network manufacturing systems make production planning, scheduling, logistics, and maintenance difficult to oversee. So the production planning and scheduling, like logistics and maintenance aspects, become more and more difficult nowadays to overlook by manufacturing managers, or it has to be handled by the people who work in the IIoT environment. So this growing complexity in manufacturing is strongly interdependent networks leads to the desire for intelligent support capabilities. The process of designing CPS might become more complex as the overall system complexity increases. Further, in cybersecurity, it is assumed that the complexity of the task can be reduced. So, by allocating the task to various manufacturing units, so having the task distributed over decentralized manufacturing units promises optimal support while allowing for a high degree of flexibility. So in order to maintain all this, the orchestration of very dynamic manufacturing systems should be adopted to improve production of individual products, including complex supply chain. So the manageability has to be improved based on these particular degree of flexibility and orchestration of dynamic manufacturing systems. So managing product and production complexity in global supply chain is a significant challenge here. So the reduction of complexity task is one of the major steps towards a smart factory using cyber technology. So, complexity appears in multiple forms, right? So, examples like complexity of the solution in manufacturing or the design or engineering processes. So, this means that there are different complexities of architecture And these architectures include software and hardware design as well as the complexity task during manufacturing. So there are so many impacts. So for considering the impacts due to the decrease in complexity of task of operation or manufacturing, it is possible to reduce cost of rescheduling, and it can decrease the effects on other products for for other reasons. Reasons like cyber technology, such as the ability of automatic scheduling, reduces the complexity of tasks and makes reconfiguration, and it also provides rescheduling and maintenance easier and faster. But at times, the ability of automatic scheduling reduces the complexity of tasks, which makes reconfiguration again and again. So rescheduling of processes, maintenance can be a tedious task. So thus the time to convert to the alternate operation is increased, and rescheduling costs can also be increased. So these particular architecture and standards could reproduce its complexity, the production of different products during the operation, maintenance, configuration, or optimization might become an easier task. So if we are implementing all these reference architecture and standards, so even then some reference architecture and standards is not adapted, then the maintenance, configuration, and optimization can be a tedious task. So, however, the process of designing cyber physical production systems might become more complex, right? So, as the complexity of the overall system increases, it can be compared to the conventional systems. So, the complexity increases, and there are so many challenges based on rescheduling, reconfiguring, and maintenance, etc. And next, moving on to cost and accessibility for SMEs. So SMEs are nothing but medium-sized enterprises. So we'll see how cost and accessibilities for SMEs can be managed. And there are some challenging factors concerned in cost and accessibility of medium-sized enterprises. So reducing the cost of ownership and training in complex engineering information is a major challenge for small and medium-sized enterprises. So the high cost for verification and validation for complex systems can be prohibitive, and considering the complex systems, the subsystems, and the component interactions in the smart manufacturing systems make it challenging to determine the specific influences, right? So when you consider each of the process performance, especially during some disruptions, there are simultaneous operation of complex systems within the factory, which also increases the difficulty to determine and resolve failures due to unidentified information flow relationships. So there is no uniform process that guides sensing, and it controls at all levels. So these particular proprietary solutions exist that integrate some manufacturing systems, but they apply to subsystems and systems from selected vendors and are often expensive and inaccessible to smaller manufacturers. So, considering the reduction of cost of ownership and training, affordable solution for small and medium-sized enterprises are possible, but reducing the cost of ownership and training in complex engineering information system is emerging a major challenge even in technologically advanced countries. So, this is the major concern here. So moving on to the next part, high cost of verification and validation. So checking and testing composability and other compatibility issues. We need more and better tools for automation, and the process of checking and testing complex systems are to be considered, and they are composed and integrated into larger systems. So these are the major concerns: the checking and testing of composite systems with better automation tools are needed here to enhance complex systems. So next we'll see what are the challenges on ongoing research needs. So first we'll have some basic ideologies in the research fields. Smart requirements engineering is needed. Dynamics of interacting multi-domain systems are possible. And third, we can consider visualization of and integration of humans. And next, we can consider checking and testing composability and checking complexity of processes, which can test the complex systems with the integrated systems. So moving on to this particular part, smart requirements engineering is the major concern, which can help in analyzing and communicating requirements for complex manufacturing systems. This is a major concern. So moving on to the second part, dynamics of interacting multi-domain systems. So we need more research into mathematical modeling of multiple domains and analysis of their dynamic interactions. So more research is needed into mathematical modeling and analysis. So this requires people with different subject matters expertise to collaborate and create new knowledge and tools. So next we'll move to visualization and integration. So the explosion of data requires smart visualization tools. So explosion of data in manufacturing requires smart visualization tools that will enable humans uh, to be properly integrated with complex systems. Next, we have checking and testing composability. So better tools are needed for automation process. So even then, integrating the complex systems, dynamics of integrating multi-domain systems are possible. So it can be a challenge while solving the mathematical model. So we need more research into mathematical modeling for multiple domains and analysis of their dynamic interactions. So this requires people with different subject matter expertise to collaborate and to create new knowledge and new automated tools. So the explosion of data in manufacturing requires smart visualization. So this will enable humans to properly integrate with complex systems. So reducing the cost also is a major concern. So checking and testing composability, and we need more and better tools for automation. And the process of checking and testing complex systems, they are composed and integrated into larger systems. So we can use these particular systems in certain commercial systems. So such identification does not imply recommendations on NIST. So it does not imply the products identified which are necessarily the best available for the purpose. So these are the challenges in research fields. So next moving on to safety, security and legal challenges. So first we'll consider cyber security, protecting data and know-how. So third is based on privacy and security, and the fourth is based on determining the impact of cyber security. So first we can see about cyber security. So cyber security, you have the centralized networking, decentralized networking of CPPS and smart products. So which has introduced increased vulnerability and risk due to cyber threats. So the range includes malfunctioning of machines, and it can also include endangering the work safety of the customer confidence. These particular systems and these particular attacks or cyber attacks are very alarming. So it gives some consequences which underline the need for reasonable cyber security solutions. So when you consider security concepts, reliable security concepts should be adopted. So it should consist of measures both on individual system participants level as well as on the overall systems level. So protecting data and how. Here that is also a major concern here. There are so many data which can be communicated in the industrial network. So we have exchange of data between companies, and we can have exchange of data in various fields. So the protection of data and how well the data is protected from the external attack is much more difficult to achieve in an decentralized system. It's a very tedious task in adaptive network also. So security is therefore an essential requirement for the successful implementation. So thus it needs to take place primarily between systems trusting each other in the sense of certificate exchange, etc. So trust has to be adapted. So to improve its safety. So identity, integrity, and encryption are thus are should be considered, and it can enhance the security of networks. So these are the major concerns here. So next, moving on to the data privacy and security. Security is therefore an essential requirement, right? So for the successful implementation of cyber physical systems, we have communication that needs to take place primarily between systems trusting each other, right? So especially when data is stored and processed on cloud solutions, it can be operated by third parties. So whenever a sensitive information is communicated in the IIoT, the sense of certificate exchange, etc., trust associated with greater safety has to be maintained. But the thing is, the privacy and security concerns are still an issue here. So identifying, integrating, and encrypting all these data with some properties which will be essential for security of networks. So, quantitatively determine the impact of cyber security. So, it should also increase its real-time performance, resource use, reliability, and safety is a key research area. So, yeah. So here, besides with these wide distribution of mobile devices, it is the people's familiarity with while using such technologies. So it can be used in private and professional contexts, which leads to the expectation of high acceptance and adoption rates. Uh, so human machine interfaces for cyber physical systems are considered, and it can considerably uh, has a challenge on real-time performance. So both the technical architecture and their user integration appears to provide a solid basis for the development. So the implementation of cyber physical systems in contemporary scenario based on these previous achievements and ongoing advances is really very challenging nowadays. So these challenges can also be rectified with new technologies and concepts. And next, moving on to safety and reliability. First, we'll see what is safety and security risk. The second, we'll see about the engineering safety system infrastructures. Third, robustness of complex systems. And finally, we will move on to complex component reliability. So, cyber physical protection systems provide the opportunity to allow adaptability, right? So, safety and security is a risk in decentralized networks remains an open question till now. In this sense, defining productivity, potential environment, adaptability, So that causes ability of using added value for the inactive percentage of potential productivity should be rebuilt. So through rebuildable functionalities, it can be enhanced. So still safety and security is an issue. So the second part is developing an engineering safety system infrastructures. So, especially in case of close integration, uh, value-adding networks or an interdependent system of systems can be adapted. So, it gives a widely distributed data flow in fundamental process. So, so it has to prevent all its manipulability. So the extended value in use becomes the risky factor. So it will also increase vulnerability due to cyber threats. So these cyber threats consist of data threat, uh, uh, handling of confidential data, privacy concerns, and security concerns. So, ensuring the robustness of complex systems to unexpected conditions and subsystems failure. So, so this is considered to be a lifelong challenge for engineers. So, however, there is still a need for more advanced methods for managing security and privacy and to build robustness in complex systems. So one more issue we can tell that is since intervention changes, the state of CPS elements are always changing and it should be performed in a controlled way during runtime without causing them harm to CPS system or its users. So component reliability is not always guaranteed, and this is a major concern. And systems must be resilient and adaptable to unpredictable events. So often in industrial IIoT, there are unpredictable events and unexpected conditions which can often occur in major systems or in subsystems. So this is a major concern. The design and use of CPS system with specific requirements can improve safety, reusability, or trust in the system. So, when we enhance these particular systems with proper CPS, with the resilient and adaptable events, then it can be controlled. So we have come to the final part. So we'll move on to the conclusion. So industrial Internet of Things presents a complex and interconnectedness web of challenges. So it spans technological, organizational, human safety, security and financial domains. So, building innovation communities that help companies and other employees to successfully go through its digital transformation will be a key factor for economic success. So, when maintained with sustained interdisciplinary collaboration between scientific research and industrial application, this can build a new innovation communities, right? So proactive change management. So the new complexity of digitization cannot be mastered through existing regulatory frameworks. So addressing not only technology but also organizational structures, workflow competencies, and regulatory frameworks should be considered. And modifying all these regulatory frameworks will have to fulfill certain requirements such as data protection and should have the flexibility to utilize the potential benefits. So this will enhance new and rapidly changing technologies. So, moving on to the last point, evolutionary process is not a sudden revolution. So, every time when we get feedback, it has to be improved. So, involving stepwise integration and continuous innovation helps rectifying all these challenges. So, in contrast to this overall impact, cyber physical systems are not expected to form the next industrial revolution. So, in this sense, a dramatic change in a very short time is possible. So, applying all these particular information, improving its complexity in digitalization, requiring flexibility in potential benefits for new and rapidly changing environments can be maintained, and it can also be improved. So these are the major concerns here, and it can also be rectified using all these technologies. Thank you. So we'll see in the next class, and we'll come with a new topic. Thank you.